That's right. We're getting ready to talk about the periodic table. Pretty exciting. I'll tell you, periodic table kind of gets me ready to go. Let's get ready to rumble. The periodic table, of course, really describes and gets us going with chemistry. It explains so much of what's out there. So let's really start to talk about the periodic table. Obviously, the first few things we need to do is get into the history of the periodic table. There wasn't this beautiful, well-defined, well-organized periodic table 200, 300 years ago. There was a development of it. And so let's just quickly go through a few of the real forerunners, some of the key folks that helped us get to this point where we are today. One of the first was Doberiner. Doberiner was a German who in the early 1800s recognized that there was some, what he called, triads. And the triads, as you can imagine, were groups of three. So he found elements, he found substances that were very similar to each other. Okay, they may have had the same physical properties. They might be soft metals that were easily cut with a knife, such as this first triad that I'm going to take a look at. It's lithium, sodium, potassium, all very soft metals. You can cut them with a butter knife, even though it's a chunk of a metal. But they also react with water. You put these things in water and they basically explode. So what he did was he looked at their atomic masses. So atomic masses. Okay? And so by looking at these atomic masses, he noticed something that was pretty important to this whole development of the periodic table. He noticed that if you look at the atomic masses, let me get a color here that we can see. I think yellow will be good. Lithium has a mass of 7. Sodium has a mass of 23. And again, I'm averaging the atomic masses from all the isotopes, basically about that. And potassium right around 39. You can look at the periodic table and see those masses. And these atomic masses, if you average the first and the last in this triad, in this group of three, the average is the mass of the middle one. Notice, if we take 7 and 39 and divide it by 2, of course, we add them all up, we're getting 46 divided by 2, which of course is 23, which is the mass of sodium. So very important. Now, Doberiner obviously couldn't do this with all the periodic tables, and I'm sure you're looking and you're saying, well, where else might there be? There's certainly some, and we'll see them in just a minute. But basically, he was able to group these certain triads together due to their atomic masses. So pretty important, I guess, beginning part to our periodic table. All right. Next, in terms of the periodic table and some of the forerunners, Newlands. Newlands in the mid-1800s created this law of octaves. And obviously octaves, I'm sure was listening to beautiful classical music at the time, but octaves dealt with 8 elements. So you're talking about 8 elements in this law of octaves. So what he noticed was that when you order elements, due to increasing atomic mass, then there's some similarities that happen once you go through 8 elements. So say you had your first, second, third, fourth, fifth, sixth, seventh, and eighth. After 8 elements, the 9th one is going to be very similar to the first. Okay, so if you look at your elements on the periodic table and we look at like lithium and we go through and again, it doesn't have to be number 1, let's say, but rather just a group. So let's call lithium number 1. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. Once you list those elements in terms of increasing atomic mass, you go to the next one after neon, and that is sodium. Notice that sodium and lithium are similar in their properties. So your law of octave states that when you order your elements due to increasing atomic mass, they're going to repeat after 8. Okay? So that is Newlands, I guess, tip to the periodic table. Next, Moseley, kind of about the same time, and what Moseley noted was atomic numbers, and kind of this whole atomic numbers, and which was extremely important in terms of the future as we develop the number of protons. But again, increasing order, he placed atomic numbers to their atomic masses. Pretty important. The real father of the modern periodic table was Mendeleev. And Mendeleev, 1860s, created a periodic table, and what he did was he used some of the things from Doberiner. He used some of the ideas from Newlands. He used some of Moseley's ideas and kind of put them together. And let's see if we can take a look here. Notice, and I'm using here, this is the Corrosion Doctor's website. Pretty nice website that has some information here, chemistry, a nice little website. But notice it says in 1969, just 5 years after Newlands, Dmitri Mendeleev started to publish a periodic table. This is a pretty, it's pretty nice, it's put together pretty nicely, but basically this was what the idea was. Notice that there was some use of Dobriner's triads. Notice there's some right there. We have some more right in here, calcium, strontium, and barium. There's some more here, sulfur, selenium, tellurium, etc., chlorine, manganese, bromine, and iodine. So those are some of Dobriner's triads. But then he also, like it mentioned, 5 years after Newlands, started to put these in together. There were also some important omissions, I guess you could say, from Mendeleev's periodic table. He noticed that there were some spaces, there were some blanks, there were some ideas. Notice these the way they say they circle here, this kind of these greenish ones known to Mendeleev. He did not know, for example, about gallium and germanium, so he left a blank there. Okay, but he knew, he called it ecosilicon, germanium. He knew it was going to be like silicon, but below it. And sure enough, later on, an element called germanium was discovered. So Mendeleev, pretty important to the periodic table. All right, let's see if we can go back to this. Oh, I also want to show this website, this video. I think it's pretty good. This is
So imagine for a second what the world would be like if one day a scientist got up in front of a symposium and stood at the podium and he was like, "Everybody, I've discovered a new letter of the alphabet. It is called Frudge, and it belongs between V and W. It's going to be wonderful for making a whole class of new words that will have abilities that no word has ever had before. Everybody, welcome to the world of chemistry." So a chemical element is a substance with a particular set of properties that can't be broken down any further than it's already been broken down. Elements are the building blocks of matter. They are the chemist's alphabet. But unlike the alphabet, which is completely arbitrary, why does it go A, B, C, D, E, F, G? Who knows? Who did that? It doesn't have to go in that order. Elements are actually set by laws of the universe. So sometimes, even recently, we've been able to create new ones. In 2011, we finally got around to naming some elements that were created in the 1990s. Welcome to Copernicium, also Darmstadtium, and Rotgnini. I don't know how to pronounce that one. Anybody? So we've got now 118 elements, which either just exist on the Earth or have been created in a laboratory. And unsurprisingly, it took some doing to get a system together that could organize all of that stuff pretty well. But creating a system to organize all of these elements is exactly what Dmitri Ivanovich Mendeleev did. And yeah, he was a Russian dude. Obviously, This guy was built for science, but not necessarily more so than this guy, or 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 this guy, all of whom made significant contributions to the way that Mendeleev ended up organizing the periodic table. But what Mendeleev did was almost certainly special, which is why, he has a crater on the moon named after him, and you don't. In Mendeleev's day, only about 60 elements existed, and he really needed some money, so he was writing a chemistry textbook, but he needed a way to organize all of these elements into a table. So he decided, why not sort them by weight, from lightest to heaviest? So Mendeleev started arranging elements into horizontal rows by atomic weight, but he fudged it a little bit to sort elements so that ones with similar physical properties were grouped together. When he did this, a definite pattern started to suggest itself, but only when he left parts of the table blank. And the pattern that he discovered was this. Elements with similar chemical properties either had really similar atomic weights, like platinum, iridium, and osmium, which are very hard, dense metals and sit next to each other here, or their atomic weights increased in very regular intervals, like in the case of potassium and rubidium and cesium. These are all highly reactive alkali metals, whose atomic weights are each 18 units apart. So Mendeleev could see that if he left some blanks in his table, he could arrange elements horizontally by atomic weight, and if he cut the rows just right, he could group elements with similar properties vertically in the chart as well. Mendeleev was so sort of overwhelmed by the power of his discovery here that he not only suggested that those blanks would someday be filled in, he also went so far as to predict what properties and atomic weights those undiscovered elements would have. And he was really right about his guesses. Absurdly right. He predicted the weights and properties of several elements that were discovered during and after his lifetime. Germanium and gallium, probably the most in-your-face examples. Germanium, he called eka-silicon because it was right below silicon, and gallium he called eka-aluminum because it was right below aluminum. And that is the story of how this beautiful chemical alphabet came to be, and how it is in fact much more logical and kind of a lot cooler than the alphabet that we traditionally know. So we could all give a big thank you to Dmitri Ivanovich Mendeleev. You kick ass. And if you want to learn more about Mendeleev, there's a bunch of cool information in the description. You can also ask us questions, which we'll be happy to answer, and suggest other topics for SciShow in the YouTube comments. And you can.
So I want to thank the SciShow here. It's a YouTube video for letting me show that. It's a fantastic little website. A lot of great little science video clips. So, periodic table.